All right. So, okay. So I think I will still keep it aside, data pipelining part. I think I'll get a little more context and keep it a little more detailed discussion than only the voice. Okay. So maybe I'll schedule another maybe. All right. All right. So far, let me. Okay. So Kush, we will discuss it again, maybe in a separate session. And for now, I would love to explain to you a little bit more about Spark and then trying to solve problem in Spark. Okay. All right. So in the last session, what we had done was we had gone through the basics of RDD, and we had also tried to run a couple of examples. All right. So okay. All right. So we had discussed these parts. So yes, we can, Kush, I can take you through Flink bit after Spark. All right. Because there are many important aspects to discuss in Spark that need to be covered and that need to be learned. All right. So far we have already covered what does it mean by RDD, what does it mean by transformation, what does it mean by an action. Okay. So all right. So there are transformations and there are actions. Transformations create another RDD after certain operations, and actions bring back the data to you. All right. So that is the difference between transformation and action. So unless you use a function which is an action, no, there will be no action at all. Spark will just keep on making notes of whatever transformation informations you are providing. All right. All right. Great. Great. So far we have basically went through the discussion of Spark, as in how do you submit the program and how do you run a program and what does it mean by RDD, transformations, actions. All right. So today we are going to talk about a little bit more about actions, and then we will try to understand how to run something using Spark streaming, as well as, but before Spark streaming, we will try to understand the various formats that Spark can handle. Okay. All right. Going ahead. All right. So take gives us a few elements from an array, from an RDD. Take is an action. If that RDD needs to be computed, that computation will start. All right. Next is the, all right. So we have also discussed something called reduce already, right? And reduce basically keeps on reducing two values into one and keeps on doing it again and again. All right. And we also talked about what does it mean by lazy evaluation and how does lazy evaluation improves the performance, right? Because as I gave you an example of a waiter who is waiting for your order, so that when it does the entire process in a batch, it'll be able to optimize the various operations. All right. We talked about various kinds of function passing. Then we also talked about the kind of errors that you might make while using scalar. Mean here basically we talked about be careful while passing things to your mapper or reducer or any other transformation or action, because that will hand over the entire object, that might hand over the entire object to Spark. Then we talked about how do you pass functions in Java. All right. We also talked about a function called sample. With sample, you can say that I'm looking for this much of sample out of a big data set, right? So similar to take sample is take sample, which basically combine this and this. All right. We also talked about why you will not get always exact fraction of the records. Okay, meaning if you have 100 records and you pass it 0.1%, 0.1 fraction of 100, the result will not be exact 10. It might be 9, it might be 11, it might be 8, or it might be 12, because this sampling technique does not guarantee exact number of records. All right. Sometimes you need to iterate over. You want to process the entire partition in a single shot. For those circumstances, Spark provides you. For those kind of circumstances, Spark provides you the map partitions function. Okay, so map partitions, if you, let's say you write a function called f, it'll get an iterator to the entire iterator pointing to the entire partition. Okay, all right. So all right. So map partition would help you when you want to process the entire partition in a single shot. And there is a function for ordering things, and that's called sort by function. If you have certain records and you want to sort the data by a parameter, then you use sort by function. Let's take this case. Okay. So I'll give you as well this, and I would expect you also to work with me on this. Okay. All right. So what this is a local variable. It's a list of tuples. This is a tuple. Tuple is like an array, but it's immutable, right? So all right, let me increase the font. And all right, so here we go. And Spark shell. All right, so I think it's coming up. How come it's so slow? Are too many connections causing it? Okay, so here we said var tmp. Okay, and then we said create an RDD on it, right? And then we said sort by. Now, question to you is that when you sort by here, right? Here we have to pass the key function. Key function is the function that declares the criteria. This for key function declares the criteria for ordering data, right? So here we are saying return x dot dollar underscore one, meaning this value for every value. So the sort by function will be called on every element to figure out the criteria on which we want to sort data. Okay. And then once we get the result, once we sort it based on that, then we'll get the result. So I'll show you this part. So we are saying sort and then collect. Why collect? Because collect will cause the action and bring the data this side. Okay. Yes, definitely, Karthik. So underscore means this is a tuple, right? For every tuple, your sort by is going to be called. Okay. By default, it'll give you an ascending order. If you want to change that, I'll tell you that also. Okay. Okay. So here the point to note is the sort by it should be passed a function. That function gives a key. Okay, that function provides key given each entry. It's similar to your mapper function of MapReduce, which provides the key, and that map function is invoked per record. All right. So sort by basically calls your function on every element, and whatever value your function returns, it sorts the data based on that value. Okay. X dot underscore one means give me the first value of tuple. I'll show you what I say. Let's say X equals to 1, comma 2, right? And we have to define it like this. All right. So X is a tuple containing 1, comma 2. X dot underscore 1 is first value, underscore is second. All right. Makes sense to you? So yeah. All right. If you want to order the data by second, this one, then the result will be exactly the way the input was. Okay. So a question from Saptrishi is, what does the greater than? Okay, I think this will be visible to all of you. Okay, so what does this mean by X this? This representation means, I'll try to explain this. This representation is equal to saying my function, which will get some records, and then we will say return X dot underscore one. Okay, so you are defining a function anonymously. Okay. Good. And it can be even further brief. It could be made something like this, right? So it could be made further brief like this, okay? Underscore means the value that's being passed, and then this underscore one means the first value of the tuple. Saptarishi, does it make sense to you? So this can be replaced by a single underscore. Good? All right. I'll show you, Thomas, in a while, in a little bit while. So there are some functions which are pseudo set operations, and these functions essentially help you doing the set operations, such as find the distinct, find the union, do the intersection, do the subtract, and so on. All right. Thank you, Manjunath. Okay. So if you want to produce a Cartesian product of two RDDs, you can use Cartesian. All right. RDD1, Cartesian RDD2, meaning all the values will be produced together. Okay, like this. So all permutations. So for every user one, all the three values would come. Then user two, all the three, and user three, all the three. Okay, so there'll be total 9 values. Okay, so a quick question: what does distinct produce? Anybody? Unique values, unique records. It'll be ABC. Thank you. All right. What will be the result of the following? So basically, intersection is set-based operation whereby, so this code, by the way, is in Python, which is a little more simpler than the Scala. Okay. Correct. It is A. Then what will be the result of this one quickly? So first we are having A, B, C. Then we are computing the distinct, and then we are joining the distinct values with A and D. Not joining, we are subtracting, meaning out of A, B, C, we are removing A and D. Correct. We will get B and C. You can say C and B. And if we do union of two sets, what will be the result? A, B, B, C union with A, D. All right. It'll be first set combined with second set. All right. So here this is wrong. Ideally, it should have been ABC and then AD. It will be. It is. I think it is wrong. All right. So it should have been ABC. Sorry. Actually, yeah. If you don't do this, we'll I think get only the. Okay. Yes. And so once you compute distinct, then A will be removed. And so the point which I was trying to drive here is that if you're joining this way, I think it'll be AABCD, not AABCAD. Okay. Here, to avoid that kind of situation where you have two A's in output, if you will have to explicitly say distinct, and then it will honor that part. Okay. Here, just a second. Ouch. I think let's try to do this. Let's try to do this and then see what happens. Okay. Let me try to convert this into scalar. So this will be list, right? And remove this, convert this to round. Similarly, we'll have another list, right? And we are saying something like this, right? And we are saying where, we are saying where, and we are saying where. All right, that's it. Let's see what happens. Okay, so it is actually A, B, C, A, D. So the union here is not really the union that we have learned. Instead, it is just the concatenation of the two. All right, it's just concatenation of the two. Now, even if at this point, let's say, what we do is we say A dot distinct and then union with A1. Okay, still after union it will become ABC, then union with AD. So union in case of Spark does not mean set operation. It is more like appending the records. All right. Okay, so what will be the output of boy, girl, Cartesian with good, bad? Sapna's question is, can we sort here? Yes, you can definitely sort. Okay, quickly. Yes, that's right, Saptrishi. It'll be because we are saying ADJ, then Cartesian, then noun, which means it'll be good boy, good girl, and you can see good boy, good girl, bad boy. All right. So this is the way you can generate all permutations of one RDD against another. All right. Okay. A quick question to you is, given a list of employees or list of values, right? What you have to find out is find out the values that differ by 3. How will you use Spark for this? Let me give you the example. Let's say the list is 1, 3, 1. Okay, 2, 10, 13, 9, and 7. So you have to list all the couples which are differing by 3. Say, for example, 7 and 10 is one couple. Do you see any other? 10 and 30, yes. So how would you, let's say this list is humongous. and you want to produce a list, a set of values which are differing exactly by 3. Yes? Okay. Let me just create an RDD for you out of this. We'll say L equals to SC dot parallelize, right? Then, now what should I do? This is where L. This is my list. Okay, Saptarishi says use the difference transformation. How would we do the difference transformation on RDD? All right. Yes, you are right, Manjunath. So what we can do is we can create, first, we can Cartesian with itself, right? We can say where Cartesian equals to L. Let's see if it happens that way. Cartesian L. Can we do that? Let's just check. This is my in-memory RDD. All right. Now, if we say cc.collect, we should see the results. Okay. So 1, 1, 1, 3, 1, 2. So you can see that how many values does cc would have? 49, and L had 7. Correct? So now we got Cartesian, right? Then we can, what can we do kind of a filter? Can't we do kind of, cc dot filter, right? Where underscore $1 minus underscore, or we can say this way, x, okay, x dot underscore 1 minus x dot underscore 2, and we say math dot abs greater than 3. Will this work? Let's see. We'll have to import math probably. Okay, let's see. All right. Or we can here actually say this. All right, we are doing something wrong here. Just a second. So this is going to be O and O dot collect. Correct. All right. Is this clear to everyone? Should I explain again? What exactly did I do? All right. Let me explain. So first thing, what I did was I converted the list into an RDD. So first I created this list and then passed it to parallelize to create an RDD. And then I did a Cartesian, as in produced all possible permutations. So this is CC is all permutations of L against L, meaning first value combined against all values, okay, and second value combined against all values, right? It is kind of a self join, you remember? Yes, that's right. We need to do a distinct after this. So we could also say O dot distinct and then say collect, right? Sorry, not this way. You will have to create a map function. Okay, I'll show you how to do that. Okay, I will show you. All right, here is a question for everyone. I forgot this part to ask you. Uh, Saptarshi is saying that let's remove these duplicates. You see 10, 13 and 13 and 10. So this should be only one. And then 10 and 7 and 7 and 10. What should we do to remove this? Who can help me with this? It's an interesting question. Thomas says use sort and distinct. But if I sort this data, it'll give me the same results. Sort the tuples. Yes. How do you sort the tuples? Yes. All right. I'll show you that. Let's apply a map on this. Okay. Let's apply a map on this. We'll say O dot map and it'll get a tuple, right? We'll get a tuple in the argument of the function. Or let me define a clean function here. Let's define our function is called sort tuple, right? We're creating our own tuple. And let's see if we can call sort on a tuple. Is there a function called sort? No, it doesn't have a sort here. No, it doesn't have. So we'll just create our own sort tuple function. What it'll do is it'll return a tuple of int by int. Correct? It will return a tuple which will have int by int. And let's define how should the sort tuple look like. If t underscore 1 is greater than t dot underscore 2, okay, then what do we want to do? We want to return return, we want to return, sorry, t underscore 2 like this, return something like this. Yes, something like this, right? Otherwise, return the tuple as such. Let's see if this function is okay. Is not clear to you? Did I make a mistake? We are saying define sort tuple. T is a tuple of int comma int. And let's see. Right? Now let's try to use this sort tuple here. We'll say 1 comma 2. It gave us 2 comma 1, right? I think this is better. Right? Let's try this. Okay, so for 1 comma 2, it should give us 1 comma 2, and 2 comma 3 is also good. Now 2 comma 1 is 1 comma 2. You see the difference? All we are checking in the function is if first value is less than second one, let it be that way. Otherwise, swap the value. Okay, if second value is lesser than the first value, swap the values. Otherwise, return as such. That's our sort tuple. Good. Now we can translate the entire list into that. Now, how do we translate? We'll just pass this function. And then we could say distinct, and we could say collect. Now, do you see the difference? Good. So someone has asked me that how do you break down the, I mean, what is the point of all of this? Why could we not just iterate over the list and then compute the subtraction? The simple answer is that here we are trying to assume that the list is going to be humongous. And the entire work need to be done in a distributed fashion. So here there are two aspects that we have covered, two very important aspects. One, how to do the self join. How many of you know what is a self join in SQL? Self join. Yes, joining the table with itself. Second, if you have to compare one record against another in a data set in a distributed fashion, this is what you do. Okay? And then second idea that we have covered here is in case you want to remove duplicates in these kind of scenario, you can always order the data in certain way and then remove the duplicate. All right. All right. So this is the result of our So I can give you this, and you can also give it a try when you're free. All right. So yes. So we have joined by itself. The other interesting function is fold. Okay. I'll skip this fold. I'll go to a more interesting function called aggregate. All right. So a very quick question to all, very quick question to all. Can a reduce function return different data types than its arguments? Can reduce function have different returning data type than the arguments? Okay. So let me ask you this. Let's say we have some function which takes two values as argument. This is int, this is int, and we want to return string. We want to return string. Now, can this be a valid reduce function? Is this a valid reduce function? That's right. It's not, but it is commutative and associative. Let's say instead of summing up two values, we are just concatenating these two values by comma. Okay, this is the function that we want to call. Now, the problem is the output of this function will be combined with other, and therefore it won't be possible to use this kind of reduce function, right? You remember the way we were doing? First, we will pick two values, apply the reduce function, whatever is the result, that will be used with another, right? Another call. And therefore, it is impossible to use this kind of function. Not clear? Anup, Barsa, Karthik. I can explain this part because this is something little confusing to us. Okay, let me just try to describe to you in this way. All right. So here, let's say we have 1, 2, 3, 4, right? The sum function will be called on these, and it will produce 1 comma 1. The sum function will be applied to this, and it will produce 1 comma 2. It's a string, while this is a number. It's a number, right? Now, if this function, same function, will be applied again, right? Because reduce function is called again and again, and when these two values, 1 comma 2, this is a string and this is another string, if we try to combine this in the second call of reduce, it'll give an error. Right? Because this one is a string and this is a number, and it doesn't know how to deal with it. Okay? So that's why the usual reduce function cannot be used here. So what do we do then? Then we use a generic reduce function called aggregate. Aggregate gives us three things. One, before a reduce function is applied, what initial value to assume? Okay, so let's take this case. Okay, let me All right. So what it provides is, so again, I'm taking the same example. 1, 2, 3, 4, right? This is what we want to combine together. So first lets us write something called initial value, right? And in case they are in separate partitions, okay, they are in separate partition, we can apply a function first on a partition, then again on another partition. Let's say this is one partition and this is your initial value. So first your function will be called with these two values, then these two values, and then these two values. Okay, so you will get, what will you get? Let's say this is an empty string. So you will write a function which takes an argument as a string, first argument, second argument as a number, and then you concatenate it. Okay, so it'll look like comma 1. Then you'll say comma 1, comma 2, then comma 1, comma 2, 2, comma 3. This is what will happen, right? I'll explain to you as we go. So, so one is that it lets you define something called initial value. Before the reduce start, it won't start with every value in the partition, at the first value in every partition. Instead, it will start with your initial value, whatever you provide. Okay, and then it asks you for something called a, a sequence function, as in a function which will be executed on every partition, right? And then whatever is the value on both the partition, how to combine that value. All right, I think this diagram will make it a little clear, like this. So there is a function that combines a rectangle and a circle to produce a circle. And that circle will again get combined with a rectangle, meaning integer or and a string. And then you produce another circle. Now, similarly, in another partition, this is partition 1, this is partition 2. So on each partition, your function that can combine a circle and a rectangle, meaning two different data types, initial value with the actual value of the uh, of the party of the RDD. Here it'll be combined to create circle, and so on, right? Similarly, this is initial value on another partition, and then this. Not clear? All right, let's try to concatenate the value. Okay, let's learn how to, let's say what we want to do is we want to produce a list which concatenate these values by column, right? By column. Okay. All right. So let's say we want to produce, all right. So let's say, I think a better example is the one which I'm talking here. Now question from Thomas is, what are the arguments for combination method and sequential? Let's say this is a string, this is an integer, right? So your sequence method, these are sequence method. Sequence methods are executed on every partition, while combination methods are used for combining values from all the partition. Does it make sense? So you can say that aggregate function is a highly customizable version of reduce. It provides us three controls. One, ability to define initial value from which the merging process will start on every partition. Second, the ability to define two separate functions. One, for combining the values on the same partition, and second, for combining the value from all the partitions, right? So the way the reduce would happen here, or the way aggregation would happen here, is this with the zero value, second argument with the result of the first one, and so on. All right. Now you may be so one very good use case I gave you was concatenating the concatenating the strings. Let's say you want to produce a list separated by column. One way would be to simply iterate over the list, bring the list to the local machine, and iterate over the list and concatenate with the column. That's doing it locally. All right. Other idea would be to first define, let's say, sequence function. Okay. And that will get the initial value, which is a string. Okay. Which is a string, and the actual value from the list, right? And it'll return a string. Okay. And all it'll do is return I plus colon plus V. Okay. If we can also do a little bit more things, we could say I equals to empty, then return only V, otherwise return I and this. Good. No, it doesn't work that way. It says type mismatch, so we could say to string. I hope I'm making sense to you. Sorry. So we'll have to say to string. Okay, let's just check if, let's say, we have empty, first value is empty. So what does it give us? It gives us 1, right? If the previous value is, let's say, 2, it gives us 2 colon 1. Saptarishi's question is, why do we need partition here? It's not our choice. Whenever we have data, huge data, there will be partitions. Okay? So this is a function that we have designed such that it can combine a string and a value by colon. So the overall objective is to produce a string by putting colons in between. Does it make sense to you? Then now let's define another function which combines two strings together, which is very simple. I'll say com. Okay, we can put whatever name we want. Okay, and we can say j and again string, and we would basically return I plus colon j. This is good. This is just one function we have defined We say that com, and let's say, right? So we could actually do other things like, okay, like checking the values of I and j and putting colon only if at least one value exists. But let's go ahead. That situation is not going to arise so easily. Okay, so we could say com and 1 comma 2 and 2 comma 3. No, it won't be comma. That will be coming from all the nodes. It'll look like something like this, right? So it concatenated that with. All right. So we had to write two functions. Why? Because there are two circumstances. One, where we are combining a string with integer. Second, where we are combining two strings. All right. Now let's call this method. How do you call this method? In this way. We call it in a little different way. We call it this way. We say, what is our RDD? This is our RDD, L. Okay. Aggregate, what is the initial value? Initial value is a blank string. Okay. And sequence function and the other function. All right. So D is a string where you can see this. It has got these values. The question is, why did it still put colon before that? Okay. We could actually say print. Okay, so return value is this, and we'll just print it here. All right, I'm just trying to show you sometimes how you can debug your problem. All right, so here we would be printing it somewhere. It would be printing somewhere. I think, mhm. Yeah, I think here it's printing. Here it's printing. All right, let me try to say something like this. I think that'll make more sense. Okay, so you can see that it has got only one partition. All right, here we go. Interesting. So it did the, all right. So we have to be careful because here the first call that it came to it is this one. Or did we make a mistake here? Just let me check what's happening here. No, that was right. So this method is being called here. All right, so it first tries to, okay, okay. So one of the partition has only got 1, another partition has got 10 and 13, and third partition got 3, comma 2, right? So here we have to be just careful about, okay? So how do you, right? All right, so what problem are we trying to solve, Thomas, is that when we are combining, right? So here it's combining empty with 1, right? Why is it so? Because the combining also starts with empty, and therefore, if I is empty, right? If let's say we have I same way, okay, same way like this. If I is empty, return the second one only. Don't try to combine it. Now it'll solve the problem. Okay, it did not solve the problem. Now this should look good. This should work. Now it's working fine. Yeah, I missed else. Okay, so did I confuse you or is it clear? So we define 3 things. One, initial value, right? Initial value. Second, the function that will be used to combine value on each partitions. Then the combiner, which will be used to combine values from the partitions. Okay, so all right. So it's going to let me again show you these values. Okay, so let's say, did we use 3 partitions? Okay, let me use it. Okay, this is little important. So what did we have? One, let's say 1 was on one partition, and 2 and 3 were on another. 4 and 5 were on third partition. Okay, let's say we make it black. Right? Now, the objective is to concatenate them with a column. We want to bring them together, okay? And we want to concatenate them with a column. So what we define an initial value, and that initial value is empty, right? It's an empty string. Here also, it's an empty string. The same initial value will be used on all the nodes, right? Now, the combination of these two will be what? The combination of these two will be, right? It'll be 1 as a string, okay? Then these two will be combined, right? That's what we are doing in the combination operation. If you remember here, okay? Then we get 2, and then these two will be combined. It'll be 2 colon 3, another string. Similarly, another partition, the third partition, these values will again start getting combined, which means it'll be 4, right? That's what we are using condition here. If the first value is empty, just use the second value, otherwise concatenate them, right? Good. And again, the 4 and 5 will get concatenated, something like this. Make sense to you? Now, these are three partition. This is like a big array. This is like a big array. Okay, one partition, two partition, three partition. Okay, this is something which is used for the execution part. Now we got three values: this one, and this one. Right now, the other process of combining these will start. Okay, and again the model will be same. There will be a initial value against which the combination will start. It will become again same logic, right? And then 1 combined with 2 and 3, which will be 1 colon 2 colon 3, and again combine these two. All right, so this is what is going internally when an aggregate function is called. So you can always cleverly use aggregate function to combine many values together. Okay. A question from Seek: will the partitions run in sequence? For example, in your sketch output, is it possible to get an output like 4, 5, 1, colon, 2, colon, 3? Yeah, that is very much possible. Actually, it happens in the reverse way. Okay. In some cases, it happens in the reverse way. Like you can see that here what are the values? Here 1, 2, 1, 3, 2, 10, 13, 9, 7, right? 1, 10, 13, 9, 7, 2, 3, 2. Okay. Did I make sense to you? That is very much possible, Sheikh. Good. Also, the reduction process is kind of parallel. All right. So a question from Seek is, in that case, how do we sort the output? Again, you will have to use sort by functions. All right. Good. Very good question. All right. This is kind of very interesting, another use case. So here we just did something very simple, like concatenating strings, right? The idea was to demonstrate how do you use a function which takes two different kind of arguments and then combine the results, right? Okay. Now question here is, let's say you have an RDD of some number. Let's say you have an RDD with lot of numbers. Now the objective is to find overall average. What would you do? Yes? It's a simple question. How would you find the overall average out of RDD? Yes? Yes, there will be an average function, but computing the average in a distributed fashion One would be that you bring all of this data to your local machine and then compute the average. Second is use some kind of reduce function. Yes. Okay. What Thomas is saying that we can sum up all the values and divide by 100. Yes, that's something which we can do. And anybody else has a suggestion better than Thomas? All right. So yes, that's something which we can do where we can just sum up all these numbers. It's pretty simple. All you have to do is RDD dot reduce, and then you return this plus this. Okay, right? And then you say collect divided by RDD dot count. Very simple. And it does work, by the way. It does work. You can see that. Okay, let me first try to. Oh, sorry, there's no need of collect. This is good enough. Right? So you got what is the answer? 50 is the answer. Now question is there something wrong with it? All right. So yeah, Karthik's question is, I'm not able to get and why we can't use an average function. Okay. Meaning you're suggesting that, let's say we have a reduce function, right? And we pass the average function. Let's say we define average, right? X comma y, and then the way it looks is this, right? X plus y divided by 2. That's what you mean? And then in the reduce, we can use AVG. Yes, Karthik? The average inbuilt command, where is that? Is there an average built on RDD? It's not there. Okay, so we are trying to compute the average of the values which are in RDD. Scalar would be having a average function, but for that, you'll have to bring the values back to your machine and then apply that function of scalar locally on the data. And that's what we do not want. We want to compute this average in a distributed fashion. Okay, because that's what the reasoning behind all of these libraries, what you see in Spark, Scala, and these MLlib and all of these newer library, the reason is that these libraries work in distributed fashion. And this is why computation of the average needs to be done again. We need to write a new function to compute the average. All right. So yes. So if we do the reduce based on the average, it'll be wrong because average of two average values with the third one is not the overall average, right? Because the way reduce would work is, let's say you have 1 3, let's say 1 3, let's say you have 1 3 4, right? Average of 1 and 3 is 2 and 2 and 4 is 3, correct? While the overall average here is 8 by 3, which is different, correct? Do you see the difference? Karthik, are you with me on this? Good. So basically, if we do it using reduce, we'll get the wrong results. While if we do the average of the overall, only then we will get the right results. Therefore, summing up the entire value, dividing it by count is the right way. All right. So the important part to understand is count is also a little intensive process. You can see that it has three tasks associated. If I say count, it's going to run on the cluster. So first, in the first job, this when we call this reduce function, it is an action. It's making the entire DAG executed. Similarly, when we call rdt.count, it's again making the process run. So therefore, the overall here, the process is being executed twice. Yes? Okay. All right. So computing the average is a very interesting, and it basically is an eye-opener problem for lots of things, because the first level of computation of average is doing it locally. Okay, doing it locally as in rdd.collect and then do the average. This is local, as in you bring all the data to local machine, compute the average on that. Second is using reduce. This is outrightly wrong. Third approach is this, right? This is decent, but it is causing two processes to run, right? Anu, Barsa, Jin, Karthik, Kush, Manjunath, Mohit, Nada, Nitin, Omkar, Prakash. All right, are you all with me? Because when I get into this kind of little mathematical, I get little worried that I might have lost your attention. Okay. Question is there a better option than these three? Rather than executing this, can't we compute the sum and count together? Can we do that? Can we compute sum and count in single shot? Can we use aggregate method to compute sum and count as tuple as we go in the process, right? This is what we have here. So what we define is, as we are going ahead in the process, we are computing these values. First, we define an init value, which is okay. Sum and count both are 0. Then we are saying aggregate the value on each of the partition into this init by increasing the sum by the actual value and increasing the count by 1, right? We're increasing the count by 1 and we're increasing the sum by the actual value. And once we are done with all of this, then we combine these together, right? By just summing up the two values, sum of sums of all the partitions and sum of counts of all the partitions. And then we call this. Sounds good to you? All right. Yes? No? Good. All of you are happy with this approach. So let's try this. If you want me to explain this approach in diagrammatic fashion, I can do that for you. So you can see that sum is this, count is this, right? The result we got, the D, is a tuple which contains count and sum both. So we can divide sum by count, right? And since it's coming out to be like this, so we could basically make it look like decimal. Let me make it look like little decimal. Right, now this is better. Multiplying by 1.0 quickly converts the data into decimal from integer, and therefore the division of decimal works. Yes. Okay, so all right, so what exactly did we do here? This is a very interesting discussion because these are the challenges you will face as we go forward. All right, so let me try to show you. Let's say you have 1, 3. This is 3. Let me make it look like 3. I'm really bad at it. 1, 3, and say 4. Correct? That's what we are trying to do. So first what we did was, on every node, the 0 value will be created. 0, 0 is there, right? 0, 0 combined with this is, the first value is sum, second value is the count. This variable contains two values. First value contains sum, second value contains count. Initially, count and sum both are 0, right? So we are trying to kind of gather count and sum in a single pass. So it'll become 1 and it'll become 1, right? Similarly, on this different node, 0, 0 will start. And then when 3 is combined with this, what we get? Sum is 3 and count is 1. Okay, now let's say on the third partition, we have two variables, 4 and 5. And we again start with 0, 0. So when total, how many values are there? 4 and this? It is 1. And sum is 4. Correct? And then 4 is, this is combined with 5, and 5 plus 4 is 9, and then count is 2. All right, now these are the three values which we got on the three partitions, right? Now these will be combined together. It is, again, it'll be start with 0, 0, and 0, 0 combined with 1, 1 is 1, 1, 1, 1, 1, 1 combined with 3 and 1, 4 plus 2, and then this. So what we are trying to gather is, once all the partitions have have finished, all the partitions have finished the computation of the three values, okay? Then we can basically sum up all of these three together, and we will get the value like, so what will be the sum? 1 plus 3 plus 9, that will be the sum, which is 13 is the sum. 1 plus 1 plus 2, that 4 is the count, right? So 13 and 4. Good? All right. Sounds good. Average looks like a complicated problem on distributed, right? All right. And when the life starts looking beautiful, and try to think of how would you compute median of a lot of values in a distributed fashion. Okay. And that itself is a different, is going to be a considerable amount of time to explain to me right now. Okay, now coming back to the same average problem. Now, do you think there is a problem with this approach? Who can tell me? Is there a problem with this approach? No? Karthik, Manjunath? Yes, it could be, it would be a little faster than the previous ones, but it could be, it has a security flaw, okay? It has a bug because when we are summing up the values, there could be an integer overflow, okay? There could be integer overflow here. Right, right. So those who are not aware, there was a recent bug in Java library whereby computation of the binary search of algorithm of Java library had this security bug, okay, where there was an integer overflow because we're summing up the two values and then dividing by 2, right? The way I plus j, okay, the average of 2 was computed was like this. Instead, it could have been something like this. I plus, sorry, j plus I minus j divided by 2. Okay. So anyway, that's a total different discussion. And yeah, because if I and j both are really huge, I plus j will be really huge and it could cause integer overflow. Same problem lies here as well. Yes, the return type should not be integer type. Yeah, we can make it long. Okay, we can make it long. All right, so yeah, that's a altogether different discussion. Those who are interested in solving this one, they can try. And if you have doubts, if you can, you know, instead of carrying over the sum and the count across, if we could carry over average and count, right? And then we can use that. All right. So we can take that discussion maybe separate, those who are interested, or take a look at my interview questions on Spark in one of the blogs. I'll I'll share that with you guys. Okay. Now coming back, this was the discussion on aggregate. So take a look at this approach, all of you. When you get a little free time, you can try this. Yes, thank you, Anup. All right, just that the blog would be in Python. Okay, so some of you have already used it. A easier way of doing the word count is just using the count by value function. It basically does the frequency counting, right? It has 1, 2, 3, 3, and 5, 5, 5. So when you say count by value, you get how many are 1? There is only 1. But 5 are 3 times. And then 2 is only 1 time. And 3 is 2 times. All right. So that's count by value. Now moving ahead. You can also try to get top n values. By default, it does the numeric sorting. You can use the other kind of sorting as well. Also, if you want to sort and take the data, you could use take ordered. And in the ordered, you could use the ordering like this. All right. So there was a question related to, yeah, sorting. I think that was answered. I was planning to answer it now. Okay. So if you want to take data from this after sorting it, you could use take ordered. Take ordered is little more efficient than ordering and taking it. Okay. All right. So take order can take the function, the argument like this, to which can define the ordering. Okay, you can see that. All right. Similarly, we have for each function. For each, it basically applies the function on all the elements of this RDD. Do not use for each. Okay, instead use map and reduce. For each is more like, for each is an action, meaning it basically brings down all the data to your machine and then does the for each. Okay. For each partition, again, this one we have talked about, it's similar to for each, but it calls your function for the entire partition. All right. Now let's talk about persistence, and then we will move on to the key value pairs. Okay. So let's take a break for 10 minutes and back by 9:47 p.m. IST. All right, so I'm back. Can we start? All right. Okay, so a question from Manjunath that can you upload the December 10 video? I had uploaded and okay, let me take a look at it. All right, looks like something went wrong. Nobody was able to see that? If you want to, okay, all right. All right, Kush. Okay, thank you. So I think I had uploaded. I'll take a look after the session. All right. Okay. Okay. I have not shared the location. I have not shared the location. I'll share that. Okay. I'm again and again forgetting this part. All right. I'll just have to clean it up and then make it available. All right. So we had talked about that RDD can be cached. All right, so let's talk about it. And generally, RDDs are lazily evaluated, and RDD and all of its dependencies are computed on an action. We may wish to use the same RDD multiple times during a process. During a process, we may wish to use the same RDD multiple times. In those cases, we would like to persist it. All right. Also, let's say we persisted. Persisted means cached in the memory, so that for every time we need that particular RDD, we do not need to query the sources. We do not need to recompute the entire tag. Instead, that RDD will be available as if it's in the memory. All right. So you can cache it or persist it in many ways. Right? There are two objectives of persisting. One, you do not have to recompute the RDD values. That's the first objective. Second objective of RDD caching is, let's say you want to keep it in the memory. That is also possible. All right. And if a node that has persisted in RDD fails, let's say there are three nodes, and containing an RDD, there are three nodes containing an RDD, and one of those three nodes fail. What do you do? What does Spark do at that point of time? And let's say this RDD was cached, was in memory. So since it knows how to compute the particular RDD by using maps or reduces, it will recompute that part and again cache it on some other node. All right. All right. It also provides you an ability to replicate. Let's say there is some data and you are afraid that the data, let's say there is some data which you have cached, but you are afraid that if those machines which have cached it, any of those fail, there'll be a recomputation and it might take a long time. But you want this particular RDD to be available on the failures as well. In those cases, you can define your replication factor for caching. Caching provides you a way to replicate data on multiple nodes. A question from Manjunath is, will it recompute when action is called or when node is failed? So the entire process of caching is valid only during the lifespan of a job. Okay, and a job is run when an action is called. So during the lifespan of a job, the whole process is valid. Okay, unless you are caching the data into the disk. Okay, that's another story altogether. All right, so in case node is failed and the RDD is cached, that particular piece or the partition will be recomputed. All right. Okay, so an example of persistence is this one. Here I'm using Python code for reason. Let's say you have list of so many numbers and you have 50 partitions and you are summing it up here, and then you are running the map function here on the partition, and then uh, and then right? So you're calling some parts again on this particular, basically you're summing up all the partitions and keeping that part is separate RDD. Now you're again calling another map function, you're increasing that value by 1 and then collect. Okay, now you can see that this partition 1, let's say, is going to be called again and again very frequently because let's say this is your important data. So this is going to be every time you call partition 1, it's going to compute the entire process, which seems to be a little complex. And if the whole process is called again, it would cause a lot of unnecessary steps. There is no need of these steps to be recomputed. That's where the persistence comes into picture. All you have to do is persist. Okay, there's a function called persist, as well as it provides you all kinds of options. It provides us all kinds of options, such as whether where do you want to keep the storage? Only memory and disk, all right, or memory as serialized object, okay, or memory and disk serialized object. Third one is disk only, and so on. If you append it by a number, that means a replication factor. So memory only underscore 2 means keep the data only in the memory and make the 2 copies of it. Okay, it's like replication factor for the cache. Okay, all right. Similar thing, if you want to do the persistence, here is a easier way in Scala. All you have to do is import org.apache.spark.storage and define what kind of storage are you looking for. The first flag in this class, we are calling a constructor of this class. The first flag means use disk, use memory, and whether you want to use the off-heap memory or not. Generally, you keep it false. And if you here, either you use disk or memory. If you use both, it's going to be a little more. It's going to handle the data in a more graceful manner. Then, do you want to serialize, as in use the Java serialization or not? And how many replication factor do you want? That's your serialization label. You define the storage label, and then while persisting, you pass this storage label as the argument. All right. By default, if you do not call this with any argument, empty argument, it would consider that you are trying to persist something in the memory, and you just want to keep the replication factor as 1. Okay, a question from Thomas. If I assign a RDD result to a variable, okay, meaning after an action, you get a value, right? It is also cached in memory. So do you mean that when we call an action, so do you mean here, let's take this case, where A, you're talking about A? Yeah, A is here when, unless something happens here, so A is basically a kind of variable that contains information about what kind of RDD it's going to create when we call an action. Okay, so A is in the memory, that's right. A is a kind of a pointer, not the actual data. Okay, let's go again. Let me try to understand. Thomas? No, it's a good question. All right. All right, great. All right, so here we go. So this was persistent. So it looked like this. So you just import this particular package. Underscore means everything from this particular package. Okay. In Scala, just like any other languages, you can organize your classes into packages, and this is the package name. Okay, just mark it above your class name, and that's it. Okay, and then let's say this. Now, if you say is, all right, I think there is a way to check. Okay, so a dot, what was there was a function to check whether it is persisted or not. Yeah, get storage label. Get storage label, it tells you the whether it's persisted or not. Here we are saying true, true, false, as in first one is for the disk. It is in the disk. It is in the memory of the heap. No, and then the last one. What was the last one? Last one was deserialized. That to true. Okay, and that's it. All right, so you can use the persistence label like this, meaning to optimize, just like while doing the SQL query, some of the data you want to keep in a temporary table and then do the work, right? In the same way, you could also use persistence in the same way as we use temporary table in SQL, right? You remember temporary tables and temporary variables in SQL. So the analogy is similar, so that you don't have to recompute certain piece of data again and again. Instead, use the previous computed values. All right. So that was the general concept on Spark. All right. Manjula's question is, can you give some example in which scenario which storage label is best? So if Good question. Good question. If your data is smaller, okay, but it's being used again and again frequently, then you can use the memory only. Okay. If your data is huge and you are okay with it being little slow, then you use disk only. If you are you're having big data in the partitions and you want that to be immediately available and really fast, and you're okay to for giving away some memory, you use both memory as well as the disk. Okay. The problem with being in memory is that in case a process is killed, that the data that has been persisted somewhere is gone, right? So that's the way you look at. Okay. Question from Kush is when to use off the heap. Off the heap is generally used when heap is kind of full. Okay. In those cases, you use off heap memory. All right. Now, coming back to a few more operations. So far, we have been dealing with array values. We did talk about tuples while we were sorting data. We did talk about tuples. So Spark kind of respects or kind of gives special preference, or kind of, you can say, it considers the tuples to be in a little different way. Okay. So we call the tuple the RDD. So in general, RDD could contain anything. RDD could be made of only numbers. It could be made of only strings. It could be made of text. It could be made of movies. It could be made of anything. It could be a complex object. It could be binary data. It could be anything. But Spark has certain functions available for you, which are very beneficial in case your data is in key value form. Okay, so there are certain special function operations on RDD containing key value pairs. These RDDs are called pair RDD. And how does it define key? Key is the first value of the tuple. Okay, so this is how you define the tuple. Okay, and so for example, you want to group the data by the key, reduce the data by the key, count value by the key, and so on. In all of those cases, key value pair based functions are very useful. Okay. For example, there's a function called reduce by key, meaning for each key, bring all the values and run the reduce function. That is reduce by key. Okay, that is reduced by key. For example, this is how the word count would look like. So we loaded the data from a text file and then converted the lines into one word per per record in the RDD, and then we converted into lowercase, as well as we converted it into the tuple. You see, we're converting each word into lowercase, comma 1. This is a tuple. So we are translating array of words into key value pairs. Okay, so this is how you convert a value into tuple, and then by using map or some other way, and then we're counting the data. We are saying pairs dot reduce by key, by default, the first value of the tuple is going to be the key, and then on all the values, this aggregation is going to be called. This reduce function is going to be called on every value. Make sense to you? All right. Do you want to do this? All right, let's try to do this. I think this will give all of us a more comfortable. Okay. So this is a standard word count problem. Did anybody try it yet? Looks strange. I think, hold on. I think there is something wrong with it. This is okay. Ouch, there is a double quote problems. I'll fix it. Let me try to fix it. Okay, this is okay. And let me try this one. This is also okay. This is also okay. It says the output file already exists. That's okay. This already exists. So we can remove it. All right. So yeah. Did it work for you? All right. So is the data clear to everyone? Is it clear to everyone? All right. So it has done the job. Let's take a look at it. Hadoop fs minus cat, and what was the folder name? You can see that. So it has done the computing. Okay. The last question is, can you explain the reduce by key? Okay. So basically, for all the keys, this reduce function is going to be called. What does it do? It just sums up the values. Let's say this is a cow and this is a dog. Simple, right? So what it does is it is going to break it down into let me just do it like manually, whatever it's going to do. So this is your data, right? Initially data will be such that each record will have string, right? Every record will have string here at this point. And then when we say break it down by space, which means convert it into one word per record. Okay, so now it is one word per record, correct? Next thing we are saying is reduce, then we are converting it into lowercase and producing comma 1. Okay, what does it mean by comma 1? Let me just say, I'm trying to use, a regular expression. Okay, so we are trying to create the tuple. All right, I'm trying to create the tuple. See that? So like this. So every record will be a tuple at this point. At this point, every record will be a tuple. Make sense? Now, when we say reduce by key, is going to sort this data, like this. Then it is going to combine based on the key. Based on the key, it's going to combine these records. Okay, you can think of this way. Okay, it's going to combine it and this way. See that? Similarly here. Okay, so when I say reduce by key, this is what it's going to do. And for each of this, it's going to call this function, what you have passed in argument, which means this will become a plus b, which means 2, it'll remain 1, and it'll become 2. And you get the results. Is everybody with me on this? Great. Okay. So one way to convert it into map key value is by directly loading it from the file in a certain format, or by using the parallelize function, or by basically using the map function, maybe map or flat map, whatever we want to use. We can use that for the converting things into the key value pairs. All right. So there are quite a few functions provided on top of key value pairs, right? So you can use a function like key, which will give you all the keys. For example, out of this, 1 is a key, 2 is a value, 3 is a key, 4 is a value. So you'll get 1, 3 as a result. Okay. Similarly, if you want to just extract the values out of it, you can use the value function. And if you want to just run map on only the values, then you can use map values function. Say you want to increase the value by 1. So 2 will be increased to 3, 4 will be increased to 5. Then you can use this way. So you are just calling map function on all the values of all the. Okay. All right. Sorry. So what does lambda means? This one is, I think this one is only for scalar. All right. So I might have to change things for you. All right. So this is lambda is for Python. This is for Python. Okay. So here the same functions would exist even in the case of scalar. All right. All right. Reduce by key we have already seen. Sapna's question is, what does lambda mean? Lambda is nothing but a way to create anonymous function. Okay, these are all lambdas. What you see here, whatever we have done earlier, these are all lambdas. These are lambda function, right? In Python. Although there is a huge, because lambda functions came before computing. and lambda function were kind of during the time of algebra, not during the time of algorithms. Okay, and lambda function is a great tool which led to the computing the way we see it. Okay, right. So this is what we were trying to, map values and calling reduce by key. These are pretty straightforward for you. And this diagram shows you that how to convert something into tuple, right? It's pretty simple. We are returning the tuple and that's getting saved here. I mean, this is one RDD, this is another RDD, and this tuple function is getting called so many times. All right. So on the key value RDDs, there are many functions that are provided, and therefore we can use these functions. Let's say there's a function called group by key, which means it will basically group it by the key, but will not combine the values. Okay, it's not a great idea to do that, group by key and then leaving it as such. All right. So Tad's question is, all right, I think this is what you mean here. All right. So Tad's question is, what does it mean by 1? Okay. What if I have, let's say, 2? Yes. Values will be messed up. Correct. So why we are keeping 1 as the same way? Because when things get reduced, it'll be like this. I'll just show you very quickly. So this is how it look like. For every word, it'll be like 1, 1, 1, 1, 1. Okay. Then they'll be reduced into 2. They really combine into 2 plus 1, 3, 3 plus 1, 4, 4 plus 1, 5. And this way, the same reduce function is getting called. The values are being summed up, right? Makes sense to you? So that's why while counting the way we were using earlier, while counting, we used, we did that. If we use 2, what will happen is everything will become double. Right. So this function is summing it up. Here, the function which we are using this function called reduce by key. It is basically summing it up. Okay. So there would be a function called rdd dot all right aggregate. Okay, it doesn't provide that. All right, let me just see. Okay, so I'm just wondering, if not 1, what else could we do? Because what we want to do is we want to sum up all the value just to do the count, right? So if we sum up all the ones, we automatically get the counts. So if we put, let's say, here something else, let's say capital A, will it make sense? Okay, then it'll be difficult to aggregate it together, right? Right. So for now, let's just stick with 1. because we want to sum it up, and this is probably the easiest way to do it. All right. Now, okay. So, all right, all right. Never mind. So I use that for taking. Never mind. So let's move ahead. So there are quite a few functions that are provided on RDD on based on the just a second, I've changed the audio device. Hello? Yes. All right. So reduce by key is it's making some kind of noise. All right. Is my voice coming through fine? All right. Because I hear some kind of a sparking. Good. So, all right. So we have group by key kind of functions. Then we have the combine by key. Okay. Now this is something which I was trying to explain. This is a very good use case for us. So this is when you want to do aggregate kind of function. Instead of a reduce, you want to do aggregate. All right, aggregate by the key. In those cases, you use combine by key function. And so same discussion where we provide two functions kind of create combiners, merge value, merge combiners, and so on, right? That's what it does. Okay, so let's say you have two values here, and you have three values, two partitions, 1, comma 2, and then 3. This is happening for each individual key. And first one is to convert the blue into this color. I think this is yellow. That's create combiner. Okay. So basically, in the same way, let me pick up a good example for you. Combine by key, and Scala API. All right. All right. So here there is a similar example. What you see, what we had discussed earlier, where we had, let's say, we had some values which need to be combined together, and we want to concatenate them by comma. So what did we do earlier is we started with initial value and then join things together. Here it provides us some a way to convert the value into something, and then lets us merge the values together. Okay, exactly same thing what we discussed earlier in case of aggregate. So combine by key is a similar function as provided in the as provided by normal RDD in the form of aggregate. All right. So this is okay. This is not really required. So sort by key is basically sorts the data by first value of the tuple. Let's say there is a tuple like this, and then you say sort by key, meaning it will be sorted by A. All right, and so on. If you want descending, you say ascending equals false, and so on. Right. So it's a similar to normal sort by functions. And subtract by key, as in you can, let's say you have two RDDs, one is this, another is this. You want to remove all the elements which are there in the second one. So A and C will be removed from it, only B will be left. Then you can join the two data sets based on the key. Okay, so easiest way to join the two data sets by creating tuple and then joining them. Okay, for example here, if we have this and this, we can basically join them together. Let's try it. Okay, you can see that, and by default it is the key on the basis of which joins will occur. Okay, let me try to create it, another one, so you can see that. And all right, so we got two RDDs, X and Y, and now we are saying X dot join collect. Okay, you can see that. So what it has done is it has basically joined the data based on certain values, right? You can see just based on the key. Is it clear to you? So what does it mean by join? Join is generally based on certain column. Here we are saying by default, joining is based on this particular key. And what it does is it basically combine 1 with 2, 1 with 3. Okay. Yes, I think it'll be, let me just see if, all right, let me see if it works. Just give me a second. What happened here? Okay, I just have to put one more comma here. Okay, now let me show you the results here. Okay, so 1 2, 1 3, 5 2, and 5 3. Make sense to you now? Okay, Anoop's question is, can the same result be achieved with zip? No. Zip is just zipping two records into tuple, two arrays into a tuple. As far as I knew it. Okay, all right, is this clear to you? Good. So join is important because we'll need it. Now, your question would be, what if we have to join based on some other column? Okay, so you can see that B will not go in the output. All right, good, thank you. Good question, Anup. Yeah. So now, so the next thing is that whenever we want to do the joins, there could be left join. So it does provide you with left join and right joins as well. Okay. So you can say left outer join. It does work in that way. Let me check. X dot left. So can somebody quickly take a look at, there was a left outer join. Maybe they have moved it as a function. So you can do the left outer join probably either as a part of the function itself. All right, I'll have to take a look at that. Okay, so you can join two records together by using join. And yeah, all right, so there was a right outer join. Let me see if we can say. All right, I'll have to take a look at that. Okay, now, so good. Similarly, it provides functions like cogroup and others so that you can group the data as well as join them in a single shot. Okay, count by key we have seen where we want to basically do the word count instead of writing reduce and map, we can simply say count by key. All right, so here this word count, if we say count by key, that'll be sufficient. Count by key. Okay. Count by value, I don't know. So I think there's some changes. We'll have to see what happens, I think. All right, there's a change. All right, let's say you want to look up for certain value, that also you can do. Not really, there's something wrong with it. rdd.lookup, it's not there. Okay, we'll have to take a look at these functions later on. Okay, Ted's question is, what is the difference between reduce by key and count by key? Count by key only counts. Reduce by key lets you execute any function you want as a reduce. Okay, reduce by key, it would need an argument. Count by key does not need any argument. Okay. All right. So as a quick assignment, you remember our discussion from last time regarding the project. So here Here in this folder, you have the data. You have the data of the Hadoop, the server logs. So let me show you the folder. So this folder contains access log of a server from NASA, and we have to find out the logs. Okay. So if we say, all right, let me leave it. I'll show you the data inside this folder. Let me open Hue. All right. So I think you can try it out. I'll just walk you through the code. Okay. So in this exercise, we're going to count the top. We're going to find out what are those top 10 IP address. Okay. So first thing we are going to do is take a look at this data. There is a lot of data in the form of zip. By default, when we say sc.text file, it is able to automatically unzip the data. And then we find out all the records that contain some IP address by saying this. Okay? By calling filter, right? By applying a filter. This is a function that we have defined. Then we are applying that as a filter by just removing all the records that do not contain IP address. Then we call the extract IP as a mapper. Okay, we call this extract IP as a mapper, and it basically uses regular expressions to find out the records and then take out only the IP address from it. Okay, once we are done with that, we just say reduce by key and count the total. Okay, so we basically are trying to find out the frequency of all the uh, frequency of all the IP addresses. Okay, and frequency of all the IP addresses by summing up the reducing by key. Key is the IP address, and the value is just 1. You can see it here. And just like word count, we are counting the total IP address. And once that is done, we are ordering data by the second field, which is the frequency. And then we are just taking 10 records out of it. Okay, so I would suggest that you should give it a try. The 49th slide, okay, 49th slide. And moreover, I'm copying it to you right away. Okay, and you can use it from there. There was one question. Yeah, done. All right, there was no question. So you can use this particular example, and this will be useful for you because we have similar exercises in the project as well. Okay. All right. Okay, so the other important aspect that comes is with respect to you planning your data partitioning. All right, so you try to lay out your data to minimize the transfer. Okay, it's not helpful if you need to scan the data set only once. It's good only if you are going to use a certain data set, certain RDD again and again, specifically the key-oriented operations. It is available, these data partitioning techniques are available for key value RDDs, meaning those which we have tuple and the first one is the key. It causes the system to group elements based on the key. I'll explain, don't worry. I'll explain these things in detail and we'll take a concrete example. All right. Though it does not give you the control over which key goes to which machine, but it lets you make sure that which key would appear together. Let's take a look at this particular problem. Okay, it's a classic use case of any magazine website. Let's say you have this user data, meaning you are a magazine website. Let's say you are a magazine website on which there are users and they have their subscription. They have subscribed to certain topics on your, let's say, blog or on your media website. Users have subscribed to various kinds of topics. And periodically, we combine user data with last 5 events. Okay, last 5 events. So let's say on one hand, you have user and their subscription data. And then on the other hand, the users are browsing information continuously. And you're getting these events that who has browsed which link, right? So there is something called expressed interest. The user have expressed interest that they're interested in politics, cricket, and something else. But in real, they are more interested in other things. They're spending more times on, let's say, jokes. Okay, so you're trying to figure that out. You're trying to figure that out, that what are those topics which are out of the interest area of the user, which they are spending more time on. Okay, so on one hand, you have everything saved in the database about the user. On the other hand, the events are coming to you continuously. In those cases, what you will have to do is you will have to kind of join this newly created RDD every minute. You'll have to join this with the user data. In these cases, you generally first cache user data. Second, you order the user data, keep the data ordered in a way that whatever key you are intersecting or joining with, it should be ordered in the same fashion. For example, here we are trying to say process new logs. Okay, every time this function is called, it gets new file, it reads that data, it picks up the events, and then joins this data, these two things such that it figures out what other off-topic things user is interested in. Okay, so every time the join is happening, there will be a lot of shuffling of the data. To avoid it, you generally order the user data such that it's easier to compare, right? So you basically use something called partition by. Using partition by, you can bring the data which has the similar key together, and therefore while joining the two data set, shuffling will be very less. Okay, so you always define, you can partition data, or you can apply a partitioner later so that the data gets sorted. Okay, so you can say partition by. there is always, yeah, you can define a partitioner. All right. Yeah, there is a repartition function which lets you repartition the data. Okay, and there is a function called repartition by. All right, pairs. I'm just trying to figure out, in case of a other label, you have partition by. Have they changed the method? All right, I'll have to see that. Why doesn't this work that way? Never mind. So we'll talk about it maybe later. All right. So yes. So the idea is just to partition the data, and yes, that's pretty much. All right. So let me make a note of it. We will discuss the partition by again. Okay, so we will discuss partition by. Looks like the newer API doesn't have the method. All right. So all right. So whenever we used say parallelize every time, we were just converting the in-memory data into something into the RDD, right? Or we have used, say, while we did the word count, we used the data from HDFS. So Spark supports wide variety of data. It can access data through, you can, the Spark supports the data in the Hadoop format. The input formats that we studied earlier, the input formats that were designed for MapReduce, the same library is also shipped with, same library is shipped with Spark as well. So Spark uses the input format whenever it reads data from HDFS. Okay, so it uses all the interfaces provided by Hadoop, plus many other file formats, such as S3, Cassandra, and HBase. All right, so this is the location from which it reads the data, like Amazon, HDFS, S3, NFS, as in network file system, and local. While data could be in many formats. Data could be in text file, JSON file, sequence file, or protocol buffers. Protocol buffers So we have talked about text files. Text files are normal text files, new line separated data. And JSON is again text format. Every record generally needs to be a full-fledged JSON. So the way we deal with the way we generally deal with JSON data is we load line by line and then convert each line into a valid JSON object. Then sequence file. Sequence file is there is a function sc.sequence file to load a sequence file. What is a sequence file? Sequence file is a file provided. It's a file format in which many files could be combined together, or binary data could be kept in a single file. Just like in Unix, you have tar. In Java, you have jar for Java, combining many things together. Well, we keep small files together in HDFS. It's better to keep it in a sequence file format. Then, okay, so we have protocol buffers. Protocol buffer is a format provided by Google for serialization, deserialization, and it's very efficient. Okay, it's very efficient. So you can deal with many kinds of file formats, and you can deal with many kinds of file systems from Spark. And so it provides efficient API for structured data sources, including JSON and Hive. And it basically lets you talk to Hive directly using Spark SQL. Okay, so databases and key value stores, it provides built-in third-party libraries that are built-in, as well as third-party libraries for various kinds of databases, MySQL, Oracle, everywhere you can read data from and process in Spark. Okay, so even Elasticsearch and any JDBC database. All right. So the various file formats other than text file, CSV file, JSON, and sequence file, and protocol buffers, there's something called object files, which you can say Java serialization you can use to save data. All right. And so this we have already used. We basically read the data either line by line, or if you want to read data such that every record is a tuple. Every record is a tuple, and it should contain the entire data in the value. Then you can say sc.whole text file. So what you see is in this folder there are three files: mku, u.data, u.journal, and u.info. See that? So when we load data here, it basically lets us, I'll show you this. Okay, so let's try to show you what does it mean by whole text file, because we have been using the text file for quite some time. Okay, so there we go. So you can see the input. If you say input.collect, it's going to be hues. You can see that. Okay. Let me exit. I did a mistake. All right. So basically, every record, the way we do it, every record gets loaded into a tuple. Every record is a tuple where the first value is the name, second value is the whole content. So here we are saying map values and converting the whole content into just the length. And we're printing the length values. So you can see the key is this. and value is the length. So basically, when you say sc.whole text file, the tuple that's created as a result of sc.text file contains the name of the file and the entire data. So if you have many small JSON files lying in a folder in HDFS, you use sc.whole text file. If there's a single use file, then you generally prefer either this way, or we will talk about some more. Okay, so that's the way we deal with text file. Now, CSV and TSV is just nothing but a special case of handling the text file. Okay, all you do is load the data into text file using sc.text file. You load the data such that every line is a record, right? For CSV and tab separated and comma separated and tab separate format, records are separated by new line. So you can simply read data using text file and we convert every record into values by either splitting by comma or splitting by tab. All right, that's how you deal with CSV files. Okay, and sequence file is very straightforward. You can simply say sc.sequence file and load the data into using sequence file. All right, so let's try to, okay, I don't have an example of this one, but we can try creating this file. All right, let's do this. Where sc.parallelize, and we send this. Let me just save it. So it must have been saved here. Hadoop fs minus ls. Yes, you can see that. In this folder, it has saved the data. That's good. Now, all right. It is created just now. Yes. All right. Now we can read this data. We can read this data using this way. All right. Okay, so we will continue our discussion from here tomorrow, and also keep your questions ready. Must try this, the IP problem, that this one that we have given you. Okay, you must try this. All right. Try to understand what does it mean by